Hi guys, it's your guy Olumide, and today we're gonna be solving another one of the most commonly asked tech interview question. It is the Invert Binary Tree. It is asked by top tech companies including Google, Amazon, Netflix, Meta, Apple, Microsoft, and other top tech companies. The problem statement states that invert a binary tree and return its roots. When a binary tree is inverted, it becomes the mirror image of itself. We can see in this example given this particular tree structure, this 5 connected to 2 children, 1 and 8, 1 also connected to 2 children, 6 and 7 and 6, and 8 have a right child, 4. So, and when it is inverted, it becomes the mirror version of itself, meaning that it is flipped vertically. It's like it is flipped in a vertical manner, so such that this 8 that was once to the left comes to the right, and not only 8 and every one of its subchild will come to the right, fine, and even this 4 that was once, if you could picture it like you place it in front of a mirror, you will see that this 4 also will be shifted to the left node right from the right node, and same thing applies to the this particular node here to this node which was once on the left side of the root node will become to appear on the right side of the root node, and as its child nodes. So as well as the child node of the 1 now, we also switch their positions. So the 6 comes here and the 7 comes from the left, move from the left node to the right node, as the 6 move from the right node to the left node. So this is essentially an inverted binary tree of this initial tree. To understand how we invert a binary tree algorithmically, let's focus on how the node changes after inversion, how the position of the node changes. As we can see, let's consider this particular node here, right? Let's consider this node. We see that this node 8 and 9, so this is just another example. So it is highly connected and it contains a lot of nodes, so it is very good for explanation. So if we could get how to work around this huge massive tree, definitely we will be able to understand how to work around this much smaller one. So that's why I go find this particular one. All right, we can see, let's concentrate on how 8 and 9 in this node how they are switched in this inverted tree. After the tree is inverted, you can notice that they have switched position relative to their parents, right? Look at the parent 4. Under the 4 was once node 8 to the left and node 9 to the right, but now they switch position relative to their parent, meaning that node 9 is now to the left, whereas node 8 is now to the right, unlike here. The key observation here is that this swap of the left and the right child happens to each node of the binary tree during inversion. What I mean by this is that you will see that similarly, just like how 8 and 9 switch position relative to their parents, the same thing happens to 5 and 4. Look at now, 5 and 4 having the similar parent of node 2, now switch position, so whereby 5 comes here and 4 comes to the other side. Similarly, this node 2 and 3 also switch position. So this switching of positions between left and right node actually happens to each and every node in the binary tree during inversion. So except the root node, right? So except the root node still remain the same. But as for the every other subtree, every other child node, they get even the root node, it happened to the root node, right? Because the left and the right node of the root node actually switch position. So you see that node 3 comes to the right and left, while node 2 comes to the right. So it happened to every node. Same thing we apply to node 3 now, whereby 6 was initially toward this side and 7 was initially toward this side, but now 7 now got to the left and 6 got to the right. So that's one foundational observation we can observe, is that each and every node have their left and right child switch position during inversion. It's also important to observe that when a left child node moves to the right, every node under it also moves to the right. Similar thing apply to when a right child node move to the left. Look at, for instance, now node 2 is gonna move to the left. Why? Because each node in the binary tree, we have their left node and right node switch for each other, right? And now during the switching, that node and all the children, I mean all the node under it, will follow it. Look at now, node 2 switched to the right from the left. It was in the left node here, now it's switched to the right node, right? And now everything that follows it, 5, 4, 11, 11, 10, 9, 8, all the node under it will switch accordingly. And similarly, when node 3 switch to the right and to the left from the right, this is the right node, right? This is left here. This is right here. So when node 3 also switch from the right, everything under it switch as well. This means that we are not just swapping the left and the right node value. So we are not trying to create a new node value or just switching that, okay, take the right node of node 1 now and change the value to 2, and take the left node of node 1, change the value to 3. No, it's not done that way. We are actually switching the node itself. We are particularly taking the left node of this node 1, of this root node, and setting it to its right node, meaning that we are setting the left node of this node 1 to its right node, that is to the right node of node 1, and similarly we are setting the right node of node 1 to the left node of node 1. So we can just basically say that we are doing this in place. So therefore, to invert a binary tree, what we're gonna do is that we are gonna transverse each and every node, and what we do with this node is that we transverse, we swap their left node and right node. Look at this particular node now, which is just representing a single node in the binary tree. So it has a left node, left subtree and right subtree. So we're just gonna swap it by saying swapping node.left and node.right. So, and what we mean by that is that we're gonna say node.left, we're gonna say equate it to node.right, we're gonna equate node.right to node.left. That way we have efficiently swapped it. So therefore we are now trying to tell that this particular node, or this same node here, so its left node is now right node and its right node is now left node. Since our strategy is to visit every node in the binary tree and swap its left and right children, there's no particular order in which we need to visit this node. So all we just need to do is visit, all we just want to do is visit each and every node and swap their left and right subtree, or let me say left and right node to each other. So, and that way we have effectively and efficiently invert the binary tree. So, and this therefore means that we can employ any tree transversal algorithm as long as every node is visited, right? So we can decide to use BFS, which is the breadth first. We can decide to use the DFS, which is the depth first method. So, but we're going to be tackling this problem using the depth first method. So you can decide to use BFS, but we are going to be using depth first to do it, because depth is quite efficient in doing it, and the same applies to BFS, which is the breadth first. So after swapping the left and the right side of the root node, we are now going to recursively call our invert function on the left and right side to invert each of these subtree. But it might look somehow to you what I just said now, but what I'm trying to say in essence is that when you get to this node, don't forget that we are reaching each and every node. So we are starting from the root node, right? So getting to this root node, the first node, we are going to swap his left and right side. Then what we want to do is that we want to go right into the left node and swap his left and right, and keep traversing, going into the left node, swap the left and right, then, you know, go back to this one, swap it left and right, go back to this one, so go back to this one, the right node initially, swap its left and right. We are just trying to recursively do the same for each and every node in the tree. So we are going to be seeing how to go about that in the code implementation. But if you check my previous video on the introduction to graphs, you will understand how the DFS work. Fine. If you don't understand, you are going to understand it in this video right now. So let's move on to the code implementation and see how it goes. Okay, let's move into the code implementation. So first of all, we are going to be defining our graph node class. So just like you can see in the version in the on the screen, you can see this the graphical or visual representation of our tree. So we have to represent it in code format, and how we do that is that we want to represent each single node as an object or instance of the graph node class, right? So, and we know that in our each node has some things in common. And what's that? Fine, let's pass in the self attribute first, and then we're going to be passing in value, so which is actually an integer, right? So each node we have a value. Fine, so let's set the value attribute to value, and we know that they will not always, so but they optionally can have a left and a right node. So why I say that optionally is that fine, you can see in the visual right there, you see that node 5 have a left and right node, right? Node 5 have left node of 1 and right node of 8. Node 1 have left node of 7, right node of 6. But if you look at node 7 itself, you see that it does not have a right node, or does it have? No, it does not have a left node, it does not have a right node. So because of that, we are going to be setting the left and right node to none by default. So if we wish, we are going to change it, so depending on the structure of the tree. So now let's do that. Fine, we define our node, our node class. So we are going to be creating different node which corresponds to what we can see on the version on the screen. We have the node 5, so we created it using node graph node of 5 to create an instance of graph node with the value 5. Okay, we also create graph node of 1, of 8, of 7, of 6, and of 4, right? So I think we have all our graph node created now. So now let's connect them together, just like they are in that screen. So we see graph node 5 have a left attribute of node 1. Fine. Node 5 have a right attribute of node 8. Same thing applies to node 1. It has a left attribute of node 7, and it have a right attribute of node 6. So what I'm trying to say in essence is that node 1 is connected, have a left node, which is node 7. Node 1 have a right node, which is node 6. Node 8 have a right node, which is node 4. So but it does not have a left node. So this is the essentially the structure of what you can see. So this is the code implementation of that structure you can see on the screen. So after that, okay, now that we have it, let's define our function that's going to help us invert the tree. So invert binary tree. So it's going to take in some values now, which is a node. Fine. So yeah, don't forget that graph this node are connected. So actually the root node is what you just need to have access to, so we can access the left and the right, and we can traverse through the array like that. So we are going to be having access to the root node, and also we most likely are going to be returning a node as well, which is the root node, because we are inverting the node, right? And we are inverting it in place, right? So we just want to return the root node of the inverted tree. So and I do like to, let's just call our function now invert binary tree of node 5. So this way now we are essentially passing node 5, which is the root node, into the invert binary tree function. So now let's go on now. So what we're going to do with this is that we want to check if node is none, and what we do is that we want to return none, or let's just see if not node, right? So if not node, that is if node is none, still the same thing. And why I'm doing this is because we are going to be, don't forget, we're going to be recursively calling the invert tree function. What I mean is that we actually want to traverse this whole array using the DFS pattern, and that is what we are going to be using. Like, that's what I'm trying to code right here. So and in doing this, we want to really touch this node 5, and from node 5 move to its left node, then touch from there, from this left node, still move to its left node, move to its right node, move back to node 8, move to node 4. That's how DFS work. It goes in depth first. It will first go from left node to the left node until you get to the last left node, then now move a step higher to go to the right node, then go back again like that until you traverse the whole the whole tree. So, and that's it. So there's a point whereby it has to return so that it won't result in an infinite loop, and that point is essentially a point whereby the node is none. Imagine now moving from node 5 to node 1 and from node 1 to node 7. So it has gotten to the end, so it doesn't have to go deeper into the length again. Why? Because this particular node 7 now have a left node of none. It doesn't have a left node, so its left node attribute is none and its right attribute is none. So at that point whereby the node is none, we wanna return none so that it won't keep going deeper. It won't just result in an infinite loop. Okay. So after that, what we wanna do is that for each node that we encounter, we want to set its left and right attribute, node.left and node.right. We want to set it to node.right. We want to swap it from a node.left. So this way we have essentially swapped it. So by assigning the left attribute of the current node, don't forget we're going to traverse through each node. So for each of the node, we want to get the left attribute and assign it to the right attribute. I want to get the right attribute and assign it to the left attribute. So this way now we have efficiently swapped it. So after doing that, we want to go deeper into this current node. What I mean in essence is that let's say the first node is always going to be the root node, which is 5. After swapping the left node and the right node for each other, we want to go deeper so that we can reach every other single node in the tree. So this is how we're going to do that. We just say that we're going to call the function again invert binary tree of node.left and invert. So that way it's going to traverse the whole left node, and after doing that it's going to come back to traverse the whole right node.right. So, and see, this is essentially the whole solution to this problem actually. So but fine, we can just basically return node right here. We can just basically return node right here, so we can have something to print. And when we come here, we just have to click print this. So that way now it's gonna return the head node eventually. So it's gonna return the head node because as it's navigating on and on, after going in depth, it's definitely going to return the head node. Because don't forget that function call, when we say something is recursive, it will keep treating the one that the inner function is gonna keep stacking them, right? So that eventually the first one will be the last out, and because of that the first node, which is the root node, will be the one that will be eventually returned last. Let's see how it goes. Okay, we see that this is printed. This graph object is what is printed here. Don't mind this one. No. Actually, I have the code written down at the bottom. So, cause every solution I do, I try to do it before I present it, so as to make sure that I know what I'm saying and I say it in a very much way that you will understand. Because if I'm gonna be doing it for the first time, it's possible I get the answer right, but I might not be able to explain it in a way you understand. So I have to do it repeatedly. Everything I do, I actually have done it before I came online and record this. So it's gonna be returning this function object. You will know, if you are familiar with Python, you know that anything main.graph node object at the end, this is the function object, right? So but this is not enough to explain, fine, it's correct actually, but you might not believe me and you might not believe yourself. So we need to print it, to print the output in a way that okay, we will be able to know that fine, this node is inverted already. So, and to do that now, I will just do some simply modification. So I'm going to define the function strings. So this function is going to be helping us to keep track of every node we have encountered. So, and it's gonna, we will be able to efficiently print this string. So at least string is more representable and presentable. So what I want to do is that each time we encounter a node, right, we want to add this node to the string. So we're gonna say string plus equals to string of node dot value. Don't forget that each node have a value, so the value of each node is what we are gonna convert it to a string so that we can concatenate it, and we are gonna add this symbol. So this is just a formatting. So, and after that we can easily now print string. So what I did, the string variable, what I did essentially is that as we are encountering this node, so right, as we are encountering this node, I'm trying to concatenate it into a string so that we can be sure that fine, this node has been inverted. So, and what I did is that after creating an empty string, as we are traversing the binary tree in this invert binary tree function, as we are traversing it, I'm keeping track of each node. So by concatenating and appending it, adding it to the string, and also adding this particular sign. So, but one thing is that this string, Python will not really allow it like that, because this string is defined outside. So, and we are in a function, so I have to declare it as a global as a global variable, so that the whole concatenation can work well. So, and after that I can then print strs. So let's run this function now and see how it goes. So, and this is it. We see that we have 584167 printed. And if you come back to this so if you come back to this visual on the screen here, you will see that the order in which it is printed as 584167. You will see that in that presentation it is already inverted, right? 584167. So you will see that it is actually, supposed to be 517684. That is how DFS is going to traverse it, but because we are inverting it now, it's going to be printing that as 584167. So this is how to solve the problem of invert binary tree, and I really hope you do understand it. Kindly do well to like, comment and share, and subscribe to my YouTube channel, please, I beg you, right? Thank you, and I hope you understand this. All right.